Just going to do a quick video here to talk about the dislocation related muddiest points that came up in class. So the first question was, how do you know in which direction to draw your burger circuit on screw and mixed dislocations? So we will actually use the same rule that we do with edge dislocations. So the first important thing is to find the direction of T, which is our dislocation line. And so in this picture, the dislocation line is defined to be coming out of the page. We could have easily defined it to be going into the page, but it's defined coming out of the page. And so we take that as the convention, and then we make a right-handed circuit. So if our thumb is pointing in the direction of the dislocation line, then from the starting point that we've chosen, we move around in this sort of right-handed fashion for the circuit. And then we define the dislocation line as the closure failure from start to finish. So that gives us this little arrow here, which is the direction of the burger's vector. So whenever we're dealing with dislocations, it's important that we define a coordinate system, right? So we need to label our axes so that we can agree on things like what direction is the burger's vector. In this case, this is X, this is Y, and this is Z. We could have labeled it in some other convention, for example, with X here, Y here, and Z here. That would have been fine. So we apply the same rule in finding the burger's vector for a screw or a mixed dislocation, and we can look at an example of that. So this is that in-class problem that we didn't get to, but which I handed out for you to practice, and this is a partly edge, partly screw, partly mixed dislocation. So the dislocation line kind of traces right along here. You'll notice that I have defined T, the dislocation line, to be in this particular direction. We could, again, have easily defined it to be in the opposite direction, but I didn't do that. So we define T, we pick some starting point for our burger circuit. Here I've picked it on the bottom layer of atoms, and so I'm sort of with my thumb pointing in the direction of T, moving along the bottom, up to the top, back over, and then defining the burger's vector there. And then I use the same strategy over here, where I pick a point. In this case, I did it on the top because I'm again pointing my thumb in the direction of the dislocation line. I sort of move along the top, hop down to the bottom, move back along, and I define my burger's vector from start to finish. So I'm still using the right-handed rule, pointing my thumb along the dislocation line, moving in a right-handed direction, and defining the burger's vector. One thing to note, the burger's vector remains constant. So the burger's vector is pointing up here, and the burger's vector is pointing up here. And even in the middle, where we have a mixed dislocation, we end up with the same burger's vector sort of pointing up here. The thing that's different is the direction of the dislocation line. So if we define a coordinate system where this is X and this is Y, then over here the dislocation line is in the Y direction, and over here the dislocation line is in the X direction. So we use the same process. Okay, next question. Our next question is, how would you find the stress field around a mixed dislocation? It's complicated. You'll essentially need to integrate ideas about the stress field around the edge dislocation and the stress field around the screw dislocation, and take into account that the character is actually both of those. So you are generating somewhat the stresses related to an edge dislocation and somewhat the stresses related to a screw dislocation. Thankfully, we're not going to get into that in MSE 312, but it is possible to do. Okay, so a couple of you asked about how do slip systems work in HCP. And so this is a figure which comes from our Roessler textbook. So you might want to review the book because it does explain slip systems and dislocations in HCP. We'll just sort of walk through this quickly. So This is describing the different slip planes that are possible, and then how many of them there are in a particular unit cell, and then the slip direction, and how many of them there are in that particular plane, and then how many slip systems are generated. So we have lots of slip systems wherein the Burgers vector can lie in the basal plane, which means that hexagonal plane. And so we have sort of these, the basal planes, we have these prismatic planes, and then we have these planes which are at an angle. But in all of these cases, the Burgers vector is lying in the basal plane. We also have some examples where the Burgers vector is not in the basal plane, and so these are the slip directions. If we have an edge dislocation, we know that the dislocation is moving in the direction of the Burgers vector, so that's giving us the Burgers vector. And these are the planes. In general, for these basal plane slip systems, the Burgers vector for HCP is defined as A over 3, and then this family of 1, 1, 2 bar 0 directions. And so we see that showing up sort of here and here and here and here. These are all that same direction. So the geometry is a little bit more complicated in HCP, but similarly we can define a slip system on the basis of the slip direction and the slip plane. Okay, next question. Okay, so several of you asked about the contour maps for stress field around a dislocation. And I guess one thing to say is that we don't want to get too wrapped up in this in terms of trying to read this contour map, because that's sort of not the main point. The main point is just understanding that in fact having a dislocation sitting at some point will create a stress in a material. And so we need to make sure that we sort of agree on our coordinate system, so we will use this coordinate system here. And so these contour maps correspond to the stresses sigma 1, 1, sigma 2, 2, and sigma 1, 2, and so we have to think back to our stress tensor description. And so if we have a little volume element, then sigma 1, 1 is the stress acting on the one face in the one direction, and sigma 2, 2 is the stress in the two face acting in the two direction, and then the sigma 1, 2, these are our shear stresses, which are acting on a face in a sort of different direction. So maybe the easiest one to understand is sigma 1, 1. So above the dislocation, it's going to be in compression because the atoms are jammed up by the presence of the extra half plane of atoms. And we see that here, although it's a little bit hard to read, but these stress contour numbers are negative. And so all this is telling us is that we have compressive stress up here and tensile stress down here. Okay? And the details in the shape of the contours tell us sort of how that's distributed, but are absolutely not important as it relates to what we're trying to understand here, right? What we want to know is that as we get nearer to the dislocation, the stress increases, and it actually increases kind of slowly out here, and then the nearer we get, the faster it increases, right? And same moving away. Right above the dislocation, it's a super high compressive stress, but that compressive stress fades away as we move further away from the dislocation. Sigma 2, 2 is a little bit harder to understand physically what's going on because it's this stress in the vertical direction. So I would say let's actually not bother ourselves too much in looking at that one in any detail. Let's, however, take a closer look at sigma 1, 2, the shear stress. Okay, so let's look closer at the shear stress. I have again drawn my coordinate system here because it's important that we agree on that. And I've drawn these little reference volumes here. So when the shear stress is positive, a little volume element sitting away from the dislocation would feel this configuration of shear stresses, and when the shear stress is negative, a little volume element would feel these sort of opposite shear stresses. So again, just in terms of reading this contour map, we can see that as we get nearer to the dislocation, the stress increases. So that's a main takeaway here regardless. The closer we get to the dislocation, the higher the stress gets. And then we can go around and see where is the shear stress positive and where is the shear stress negative. So in this section it's positive, over here it's positive, and also down here it's positive, and here it's positive. So that means if a dislocation is sitting at this point and it feels that shear stress is acting to make the dislocation move in this direction. So that's really all we want to take away from this. The nearer the dislocation is to the origin or the other dislocation, the higher the stress it feels, and depending on the sign of the shear stress, it will want to move in a particular direction. So we can just go ahead and finish this up. So in these other sections, the shear stress will be negative in sign, and the dislocation will feel a shear stress such that it will move in the other direction. So as we talked about in class, inside sort of this x equals y space, the dislocations move together to line up underneath the original dislocation that's sitting at the origin, and then sort of in these side sections over here, if a dislocation is sitting there, it's going to be repelled away from the original dislocation. So those are the main things. We don't need to worry too much, as I said, about actually reading the contour map, but just understanding what the value of the stresses mean and what it tells us about the state of affairs around the dislocation. All right, let's go on. Okay, so somebody asked about dislocation climb, and that's a good question. We didn't really talk about it in class. Usually, the dislocation motion we've been thinking about so far is dislocation glide, and when a dislocation glides, it moves in its slip plane. Sometimes, though, a dislocation will move out of the slip plane. It might need to move out of the slip plane to try to overcome an obstacle, for example. And so when the dislocation moves perpendicular to the slip plane, that's called climb. So this figure here also comes from our textbook by Roessler, and it's useful for illustrating what's going on. So this is the initial stage. Notice that we have an edge dislocation here. We also have a few vacancies in this structure, and the vacancies are important because they are highly involved in the dislocation climb process. So in this first step, this vacancy that's over here is going to trade places with the atom next to it through diffusion, trade places with the atom next to it through diffusion, and then essentially trade places with this atom through diffusion. But if a vacancy moves here, the atoms on either side are essentially going to just relax in, and that effectively moves our little T dislocation sign, the bottom of the half plane, up by one step. And so when we look over here in this figure, you can see that where the dislocation used to be, it's now one plane higher than where it was in picture number 1. So if we now look at this vacancy that's up here and trace its movement, it's going to trade places through diffusion with this atom, trade places here, trade places here, trade places here, and our dislocation moves up again. A couple of things to note about dislocation climb is that because it relies on vacancy motion, it happens more at elevated temperatures where vacancies can move more easily. And to understand climb, it's useful for us to think again about the stress fields around a dislocation. So it is kind of relieving the stress of the dislocation if this vacancy moves over here. So there's some additional driving force for this diffusion process to happen. So that's how dislocation climb works. We won't talk about it too much more in class, but as we talk about dislocations interacting and overcoming obstacles, we can keep in mind that this is another way that dislocations can move. Okay, our next question, does the negative in the equation for sigma 1,1 matter? And the answer is yes. Without that negative there, we would find out that there was a tensile stress above the dislocation and a compressive stress below it. So the sign is important because the sign is telling us if the stress is tensile or compressive. So make sure that you pay attention to the negative sign here and in any other equation where you might find one. So somebody asked, do dislocations really only move in close packed planes and close packed directions? Are there exceptions? Do we need to know about them? And so this figure comes from our text by Roessler, and this is the slip systems in body-centered cubic metals. And so we have the slip system that we have been focusing on, where the slip plane is the 110, which is the close packed plane. But slip is also possible with the same Berger's vector, which is that close packed direction, but on other planes. And these are not the close packed planes, but this does happen. So the answer is yes, there are certainly exceptions. We saw earlier in this video about what happens in HCP, and those are not all close packed planes, obviously, as well. In terms of do we need to know about them, I think that it's useful to know that there are different slip systems. We won't be solving problems where you need to identify these. One thing to note is that when dislocations move in close packed planes, it's a lot easier for them to move, and the stress that's needed is a lot lower. And so those materials are going to tend to be more ductile and sometimes less strong. So sort of as a generality, FCC materials are more ductile and less strong than BCC or HCP metals, kind of making all other things equal because dislocation movement is easier in FCC. Okay, one last question. Okay, so somebody asked, what is M? And M is the direction of dislocation motion. We use M to know basically which direction is the dislocation going to move, and that's important to us because if a shear stress is applied, we want to know what's going to happen essentially in the material. I do have a whole video on dislocation motion, so if this is your question or you also have this question, I would encourage you to rewatch that other video. So I hope this has helped to address some of these questions related to dislocations, and we'll see you soon.